Hey guys, so now we're going to do another example, but with quadratic on top and on the bottom of the rational, so just a little bit more complicated. So first step here is to look at the question. The question is obviously you have two quadratics, and it has to be greater than 0. Okay. So first thing, just to make it a little simpler, factor both top and bottom. So we need two numbers that multiply -2 and add up to -1, which is x -2 and x plus 1. On the bottom, two numbers that multiply -12 but add up to positive 1. So that would be x plus 4 and x minus 3. Okay. So just looking at here, you can see that the denominator can't be equal to 0. So our asymptotes are going to be positive 3 and -4. Okay. To find our horizontal asymptote, okay, we look back to our original function and we just set x equals to positive or negative infinity. So, but first we got to rewrite this in different form. Okay, so I'm going to divide top and bottom by x squared. Okay, so I have x squared divided by x squared, which is just 1 minus 1 over x minus 2 over x squared divided by 1 plus 1 over x minus 12 over x squared. Okay, is equal to, say, fx. So when I put f of infinity, okay, I have 1 minus 1 over infinity minus 2 over infinity over 1 plus 1 over infinity minus 12 over infinity underscored. Okay, so any number that's over infinity, okay, just crosses off to 0. Okay, so this becomes 0, this becomes 0, this becomes 0, this becomes 0. So in the end, we're left with positive 1. Okay, so that's the end behavior. Okay, so as f approaches positive infinity, okay, the function approaches 1. Okay, and now to do the negative infinity, okay, it's the exact same thing except these are all going to be negative, so therefore it approaches 1 as well. Okay, so our horizontal asymptote is y equals to 1. Okay, so that's that. So we gotta now kind of figure out for which intervals is this function positive or negative. Okay, so we're gonna build. Actually, first before we do that, let's find the x-intercepts. Okay, so these are the main important things right now. We have our vertical asymptotes, our two vertical asymptotes, and then we have our horizontal asymptote. Okay, and now we got to find out what our x-intercepts are from this equation. Our x-intercepts are 2 and -1. That's just looking up here. These two brackets, you just find the two roots of them. Okay, so the root of that is just 2 and -1. So these are our x-intercepts. Okay, so now if we build our sketch of the graph, okay, we have our horizontal asymptote, so I'm going to draw this with different colors. So there's our horizontal asymptote of the value of y equals 1. We have our vertical asymptotes of 3 and -4. Okay, so here is 3, here is -4. And we know that it'll pass through two intercepts, or x-intercepts, which is 2 and -1. So that would be here and here. Okay. So we know that our function will pass through those 2 points there. Okay. So just by looking at here, you can see how there is like a kind of a cage for this area of the function down here. So you know the function is gonna ride along this asymptote, pass through that, pass to the other x-intercept, and finally ride down this asymptote. Okay. So now what we got to do is kind of figure out if the function is positive or negative after this asymptote, and positive or negative before this asymptote. Okay. So this asymptote has a value of positive 3, so we'll sub in a value of, say, 4. Okay. So if we sub in a value of, say, 4 in here, we get 4 minus 2, 4 plus 1, x plus 4, 4 plus 4, and 4 minus 3, which is 2, 5, divided by 8, and 1. Okay. So this is going to be some positive value. I don't care what the value is, but it's a positive value. So it'll be up in this. Actually, yeah, we do care what the value is because it has to be. We have to figure out if it's above or below 1. Okay. And so then it's going to be 10 over 8. So obviously it's above 1. Okay, so this is greater than 1. So it's going to be in this region of the 2 asymptotes. Okay, so we just sketch this curve here. And finally, we got to figure out where it is on the left side before negative 4. So we got to put in negative 5 in here. Okay. So I'm just going to erase all this stuff. So we have negative 5 minus 2, negative 5 plus 1, divided by negative 5 plus 4, okay, and then negative 5 minus 3. Right? So this becomes negative, what is this? Negative 7, negative 4, divided by negative 1, and negative 8. So 7 times 4 is 28, I'm pretty sure. And I'm left with positive 8 on the bottom. So this is also greater than 1, right? So that's going to lie somewhere in this region. So I'll just finish this sketch here. And there you go. That's our sketch of this function. It's pretty ugly. But the original question, I already forgot what it was. It's when this function is greater than or equal to 0. So I'm going to highlight that region there. It's going to be pretty much this section of the function and this section as well as this section. Okay, so everything on the bottom you don't really care about. So obviously the intervals for which that is true is anywhere to the right of that value, and anywhere oh sorry, no, I was wrong. Erase that. So the region where it's true is anywhere above this value. Actually, okay, you see where if I go anywhere to the right of this 0, the function is above 0, right? And anywhere before this asymptote. Okay. So using my bracket notation, this interval can be denoted by negative infinity and what was negative 4? Let me check. Yeah, negative 4. Negative 4. Okay, so that means anywhere before negative 4. And finally, for this region, we need to find out what that x value is. And that x-intercept was negative 1. Okay, so this interval can be denoted using negative 1 and positive infinity. Okay, so that's the answer. That. So those are the 2 regions where the function is positive. And that's how you solve it graphically. There's a whole bunch of ways, but I find that sketching, like building the basic sketch of the graph, is the easiest way to go about these types of questions. Okay, so thank you. It's done.